Alternating current naturally oscillates between positive and negative values. To convert this into a usable DC-like signal for electronics, we use full-wave rectification, which flips the negative half cycles to positive ones. Let's explore how we calculate the average value of this new waveform. In a full-wave rectifier, the bridge circuit ensures that current flows through the load in the same direction during both halves of the cycle. This results in a pulsating DC output where the negative voltage peaks are reflected across the x-axis. Notice that the frequency of the pulses is now double that of the original AC input. Instead of a full cycle from 0 to 2 pi, we now have a repeating pattern every pi radians. This repetition is key to calculating our mathematical average. The mean or average value of a periodic function is defined as the area under the curve for one cycle divided by the length of that cycle. For a rectified wave, we calculate this over a half period, from 0 to pi. The instantaneous voltage is represented by the peak voltage Vm times the sine of omega t. Since the full-wave rectifier makes all values positive, we are essentially integrating the absolute value of the sine function over our interval. We pull the constant peak voltage Vm outside the integral. The integral of sine theta is negative cosine theta. We must now evaluate this expression at our upper limit of pi and our lower limit of 0. Substituting the limits, we get negative cosine of pi minus negative cosine of 0. Since cosine of pi is negative 1 and cosine of 0 is 1, the term inside the bracket simplifies to 1 plus 1. The result is 2 times the peak voltage divided by pi. This means the average value of a full-wave rectified signal is approximately 63.7% of its peak value. This is a constant ratio for any pure sinusoidal input. If you were to level out the humps of the rectified wave into a flat line that contains the same area, it would sit at exactly this height. This average value represents the equivalent DC voltage for applications like battery charging. Let's look at a practical example. If we have a peak voltage of 170 volts, which is common in 120 V RMS household power, the mean rectified value is 2 times 170 divided by pi, resulting in approximately 108.2 volts. For a lower voltage system with a 24-volt peak, we simply multiply 24 by our constant 0.637. This gives us a mean value of 15.28 volts. This calculation is essential for sizing components in power supplies. It is important to note the difference between rectification types. A half-wave rectifier only uses one half cycle, resulting in an average of Vm over pi. The full-wave rectifier is exactly twice as efficient in terms of average voltage output. Does frequency change the mean value? No. While the pulses occur more often at higher frequencies, the ratio of the area to the base remains the same. The mean value depends only on the peak amplitude of the wave. In real-world circuits, diodes have a small voltage drop, usually 0.7 volts each. In a bridge rectifier, the voltage passes through 2 diodes, so the actual mean value will be slightly lower than the theoretical calculation we performed today. To summarize, full-wave rectification provides a continuous series of positive pulses. By integrating the sine function over the interval of pi, we find that the mean value is always 2 times the peak voltage divided by pi, or approximately 63.7% of the peak. Test your knowledge. If the peak voltage is 100 volts, what is the mean rectified value? If you calculated 63.7 volts, you are correct. Remember, 70.7 volts would be the RMS value, which is a different calculation entirely. Understanding the mean value is the first step in designing efficient power conversion systems. You can now calculate the DC equivalent of any rectified sine wave. This lesson was generated by Vision Solve AI.